Jai Hind students, welcome to my YouTube channel. Students, in this particular experiment, we will be using a hollow prism. A hollow prism allows us to change the liquid inside and thus change its refractive index. We'll be filling this hollow prism with various liquids, starting with water, dilute sulfuric acid, vegetable oil, glycerine and vinegar. And by filling the prism with different liquids and measuring the deviation for each, we can compare how much the light is bent and determine the refractive index of each liquid. At first, let us consider the hollow prism to be empty. That is, it is unfilled or containing air. The medium inside the prism is the same as the medium outside. Now, because the refractive index of the internal medium, that is air, is essentially the same as the external medium, which is again air, therefore light passing through an unfilled hollow prism does not undergo significant net deviation or change of direction. Students, now let us fill this hollow prism with water. Now, by filling the prism with water and measuring the deviation for it, we can find out how much the light is bent and determine the refractive index of water. Now look, I am indicating the spot on the graph paper. This will indicate the deviation of light when passed through water. Now let us fill the hollow prism with dilute sulfuric acid and repeat the same step. When the light is incident, the emergent ray will get deviated. Here the deviation is slightly greater than that in the case of water. Now students, let's repeat the experiment with the same incident angle but with different liquid. In this case, we are considering vinegar. So at an angle of incidence of 30 degree, here the emergent beam is getting deviated. But in this case, the deviation is found to be slightly less than was in the case of water. So that's the spot. It is on the left hand side of that of water. So obviously vinegar is slightly less optical denser than that of water. Now let us consider the refraction of light through a glass prism. So glass is an optically denser medium. So here when the light is incident, then the emergent ray get deviated through large angle. So there's this spot on the screen. So the deviation suffered by the emergent ray is much larger as compared to the other cases. It has to be noted, students, that greater the refractive index, greater is the deviation suffered by the emergent ray. Students, now let us fill the hollow prism with vegetable oil. Now we are aware hollow prism filled with different liquids will cause the light spot on the screen to deviate by different amounts because each liquid has a different refractive index which affects how much light bends. When a light ray passes through a prism, it deviates. Now for the same angle of incidence, in this case the deviation suffered is less than that of glass, but more than that of water, vinegar and dilute sulfuric acid. So that tells us regarding the relative refractive index of vegetable oil. Let us summarize the entire thing. This is the spot for vinegar, this is for water, this is the spot for dilute sulfuric acid, this is for vegetable oil, and that's the spot obtained in case of glass. The spot towards right indicates greater deviation of emergent ray, indicating greater refractive index of that particular substance. So students, this is the setup which I have used so as to study the deviation of the emergent ray when incident rays pass through a hollow prism which is filled with various liquids. This is the source of light. Laser, it stands for light amplification by stimulated emission of radiation. It acts as a source of monochromatic, highly intense, coherent beam of light, right? So I've ensured that while performing this experiment, the angle of incidence in each case is considered to be 30 degree, right? And there's an equilateral hollow prism, angle of prism would be 60 degree. And in case the hollow prism is unfilled, then the ray will remain undeviated and it will hit the center. The spot will be obtained at the center of the screen. Now students, if we consider the case of a vinegar like this, this is what I performed the experiment, which you must have seen through the video. Now this is vinegar and angle of incidence is taken to be 30 degree. Now here the spot is obtained over here. This is the spot which is obtained on the screen like this. It gets slightly deviated from its original path, right? And students, at point A, on measuring the angle of refraction, in the case of vinegar, it's found to be 22.5 degree. So directly applying Snell's law at point A, which states that refractive index would be equal to the ratio of the sine of angle of incidence to the sine of angle of refraction, the refractive index of the vinegar can be easily determined, right? So this is the case of a vinegar. Similarly, students, I've considered the case of water as well. So in this case, the angle of deviation that's found to be slightly greater than that was in the case of vinegar. So here this spot is obtained somewhere just below the water. So in this case, the deviation is slightly greater. Here again at point A, I have determined the angle of refraction, which comes out to be 22 degree. So directly applying Snell's law at point A, sine 30 divided by sine 22, that must give us the refractive index of water, right? Similarly, students, I performed this experiment for glass as well. Now glass is a solid, right? I've considered this experiment by using a glass prism. Now glass, it's a solid, its refractive index is high. It is about 1.5, isn't it? So what I've done is, by using glass, I've not shown over here the deviation, but in this case, the deviation suffered by the emergent ray would be maximum. You can notice, now using glass, the spot would have obtained somewhere over here, right? It would have deviated through maximum amount because its refractive index is high. The greater the optical density of the material of the medium, the greater will be the deviation suffered by the emergent ray. And the spot will get deviated through that much larger amount, right? So this was for glass. Similarly, I performed the experiment or this investigation by filling the hollow prism with dilute sulfuric acid. In this case, students, the deflection obtained is greater than that of water, right? So its refractive index needs to be greater than that of water, right? And here the angle of refraction is found to be 21.5 degree. And as I've told you, directly by applying Snell's law at point A, which is mu is equal to sine 30 divided by sine 21.5, we can easily determine the refractive index of dilute sulfuric acid. By using Snell's law directly at point A, we have determined the refractive index of various liquids. That we will show in the next slide, right? And lastly, students, I've also used this vegetable oil, right? In this case, it is having slightly greater refractive index than that of dilute sulfuric acid. So when I've done this experiment by using or by filling the hollow prism with vegetable oil and making the ray of light incident at an angle of 30 degree, then the spot is found to be obtained somewhere over here. So in this case, the spot, it gets deviated through larger extent, indicating that the refractive index of vegetable oil must be greater than that of dilute sulfuric acid. The greater the optical density of the liquid, the greater will be the deviation suffered by the emergent ray, and the greater is the extent through which the spot will be obtained from the center of the screen, right? So this is an increasing order of the refractive index or the optical density. Vinegar, its refractive index is about 1.32. I'm talking about the actual value. Water, it's 1.33. Dilute sulfuric acid, it is about 1.36. And vegetable oil, it varies. It is from 1.45 to 1.47. And glass, it is 1.5. So it will get maximum deviated. Now let us determine the refractive index of various substances starting with glass. In order to perform this particular experiment, we will be requiring a glass prism, a drawing board, a sheet of paper, drawing pins or paper pins, a protractor and a scale. Initially, we will fix
a sheet of paper on the drawing board with the help of drawing pins, and then we will draw a line in the middle of the paper and place the prism such that its face is parallel to the drawn line. Now students, we will draw its boundary with the help of a sharp pencil. Now after removing the prism, we will draw a normal roughly at the center of the refracting face. Now students, normal is an imagined line drawn perpendicular to the surface. Now using a protractor, we will draw a line which is making an angle of 35 degree with the normal. Now this line will act as the incident ray, and the angle which this incident ray makes with the normal, that is the angle of incidence. Now we need to fix 2 pins on the incident ray, and it is to be ensured that the pins are fixed vertical and with a minimum separation of 8 to 10 centimeters. And thereafter we will put the prism back in its position and then look for the images of the pins P and Q through the refracting face. Students, the images of the 2 pins which are fixed on the incident ray can be easily seen through the second refracting face of the prism. Now we need to bring the images of these 2 pins in a line, and we need to fix a 3rd pin so that all the 3 pins lie on the same straight line. I repeat students, we need to fix a 3rd pin so that it is in line with the images of the earlier 2 pins. Now it's perfect. So now you can check all the 3 pins are lying in the same straight line. Now students, after this we need to bring the images of the 2 pins on the incident ray with the 4th pin, so that it is also in line with the other 3 pins. This is perfect. So all these 4 pins must lie on the same straight line. This is the most important aspect of this particular experiment. So it needs patience, and you need to laterally shift your eye and check. There can be only one unique position where all the 4 pins lie on the same straight line. After this students, we need to remove this prism, and then we also need to remove the pins one by one. After that students, we need to encircle the positions of the 4th pin. Then similarly we need to encircle the position of the 3rd pin, and then the positions of the pins on the incident ray. Now students, what to do is, we need to draw a line joining the positions of the 3rd and the 4th pin. So this is the line. This will represent the emergent ray. Don't forget to indicate the arrow. Now students, we need to draw a normal at this particular point. Normal is an imaginary line which is perpendicular to the surface. Now let us produce the incident ray. Now students, in the absence of the prism, the incident ray would have travelled along this straight line as per the rectilinear propagation of the light. Also, let's produce the emergent ray in the backward direction. The angle which the incident ray when produced makes with the emergent ray, that is the angle of deviation. So this is the angle of deviation which I am representing by del. Angle which this emergent ray makes with the normal, that is what we call as the angle of emergence. We will represent it by small letter e.
Corresponding to the angle of incidence of 35 degree, the angle of refraction is obtained to be 19.5 degree. We will repeat the experiment for vegetable oil. That is, the hollow prism is now filled with vegetable oil and then the process is repeated. We need to fix two pins on the incident ray and then from the opposite face of the prism we need to fix two more pins so that they appear in line with the images of the earlier two pins. Ensure the correct alignment of the pins and their images so that the path of the light ray can be accurately traced. Now students, mark these points and on joining these two dots, we will obtain the emergent ray. Corresponding to the angle of incidence of 30 degree, R is obtained to be 20 degree. Now let us determine the refractive index of water. So we will follow the same steps. The pins are to be fixed on the incident ray and then we need to ensure the correct alignment of the pins and their images. So as a result, the path of the light ray will be accurately traced then. Now students, the observer needs to look through the prism from the opposite face to see the images of the two pins fixed on the incident ray. So the two pins and the images of the pins on the incident ray all must appear to be in a single straight line. Now students, we need to remove the pins and encircle the points, and then removing the prism we need to join those dots. This will actually represent the emergent ray. And the refracted ray can also be traced by joining points A and B. Corresponding to the angle of incidence of 30 degree, the angle of refraction is obtained to be 22 degree. And this is the summary of the observations which we have just now discussed. In the case of water, vegetable oil, vinegar, dilute sulfuric acid, we have taken the angle of incidence to be 30 degree. While in the glass, I have taken the angle of incidence to be 35 degree. And this is the angle of refraction obtained in the first refracting phase of the prism. So directly by applying Snell's law, sin I divided by sin R, we can easily determine the refractive index. This is, students, the experimentally obtained value of the refractive index of these liquids and glass respectively. And this is the actual value. Now let's plot graph between I and del for various liquids and determine their refractive indices. So students, this is the result which we have obtained in the case of vegetable oil, right? So this is the graph between angle of deviation and the angle of incidence. It's pretty clear that initially as the angle of incidence is increased, the angle of deviation decreases. Corresponding to a particular value of angle of incidence, the angle of deviation attains minimum value. And thereafter, if the angle of incidence is still further increased, the angle of deviation starts increasing. So this is the graph between del, which represents the angle of deviation, and the angle of incidence I. So from this graph, the del m, that is the deviation which is have minimum value in the case of vegetable oil. So it's found to be 34 degree. Now this is the working formula so as to determine the refractive index of vegetable oil, right? So sin A plus del m by 2 divided by sin A by 2. That will give us the refractive index of this vegetable oil. So let's do the needful calculations. Now students, angle of prism, here we have considered a hollow equilateral prism. So the angle of prism is 60 degree and del m, which is the minimum deviation angle, in this case is found to be 34 degree. So substitute this value over here, what we get is mu, it's equal to sin A plus del m, which is 60 plus 34, 94 by 2, that is 47 degree, divided by Angle of prism is 60 degrees, so sine A by 2 would be sine 30 degree. So sine 47 degree, it's approximately 0.7314. And sine 30, it's half, that is 0.5. So on solving it, students, the refractive index experimentally by plotting graph between angle of deviation and angle of incidence and getting the value of del m and using this formula is obtained to be 1.46, which is in close agreement with the refractive index of the vegetable oil determined by other method as well. In case of water, again, the nature of the graph obtained between angular deviation and the angle of incidence is same as was in the case of vegetable oil. That is, initially with the increase of angle of incidence, the angular deviation decreases. Corresponding to a particular angle of incidence, the angular deviation attains minimum value, and thereafter if the angle of incidence is still further increased, the angular deviation starts increasing. So nature of the graph obtained for any liquid would be same, right? So here from the graph, it can be easily determined that the angle of minimum deviation in case of water, that is found to be 22 degree. So substituting this value of del m over here and knowing the value of A, which is 60 degree, we can easily determine the refractive index of water. So as we are using an equilateral hollow prism, right? So angle of prism is 60 degree and minimum deviation angle in case of water is experimentally determined to be 22 degree. Therefore, refractive index, it would be equal to A plus del m by 2. So 60 plus 22, that is 82 divided by 2. So it will be sine 41 degree divided by A is 60 degree. 60 by 2 is 30. So divided by sine 30 degree. So sine 41 degree, from the trigonometric table you can check, it's about 0.66. Divided by sine 30 is half. It can be written as 0.5. So on solving we get 1.33. So the refractive index of water as determined by this method is found to be in total agreement with the actual value of the refractive index of the water. In case of dilute sulfuric acid, that is dilute H2SO4, again the same thing was performed, the same experiment was performed. The hollow prism is filled with dilute sulfuric acid, and then for different angle of incidences, the corresponding different values of angular deviation were calculated, right? And then the graph is plotted between these two, angle of incidence and the angular deviation. And the nature of the graph obtained is like this. Again, it represents the same thing. Initially, with the increase in I, the value of del decreases. Corresponding to a particular value of I, it attains minimum value. And then on the further increase in the value of I, the angular deviation starts increasing, right? So here from the graph, the angle of minimum deviation, this must be the angle of minimum deviation, that is found to be 25 degree. Right? So again, let's substitute this value over here. Angle of prism, it is 60 degree, and angle of minimum deviation in the case of dilute sulfuric acid is determined to be 25 degree. So refractive index, it's equal to sine A plus del m by 2 divided by sine A by 2. So let's substitute this value of del m and A over here. So 60 plus 25, that will give us 85 divided by 2. So that will give us sine 42.5 degree divided by A by 2 would be 30 degrees. So divided by sine 30. So again, using trigonometric table, sine 42.5 degree comes out to be about 0.676, and sine 30 degree it's 0.5, half. So the value of refractive index of dilute sulfuric acid is determined to be 1.352. So it is slightly greater than the refractive index of water and less than the refractive index of vegetable oil. Now let's calculate the value of refractive index of vinegar. Again students, we need to plot graph between angle of incidence and the corresponding value of angle of deviation. And here in each and every graph, don't forget to mention the scale. Along x-axis, we have considered one division, which is 1 centimeter, to be equivalent to 5 degree, 30, 35, 40, 45. And this is the kink which I have represented over here. This is also a kink along y-axis. Along y-axis students, 1 centimeter, that is one division, this one box, that represents 2 degrees. So that is 20, 22, 24, 26, 28, 30 and so on. So while plotting graph, mention the physical quantity which you are representing along x and y direction, and also don't forget to mention the scale, right? So again, the nature of the graph, as was obtained in the case of vegetable oil, as was obtained in the case of water, as was obtained in the case of dilute sulfuric acid, it's the same thing. It tells the same story. That is, initially with the angle of with the increase in the angle of incidence, the angular deviation first decreases, it attains minimum value, and thereafter with the further increase in the angle of incidence, the angular deviation starts increasing. So from this graph, the value of del m, it can be easily determined. Now look, it is pretty clear that del m in this case is between, this is 22, 24, so the midpoint is 23, and 23, 24, its midpoint is 23.5. So angular deviation minimum, I'm talking about del m, the minimum angular deviation in the case of vinegar is found to be 23.5 degree. So we need to substitute this value over here. The angle of prism, it is 60 degree as we are considering hollow equilateral prism, and del m, minimum deviation angle in the case of vinegar, is 23.5 degree. So substituting the value in the above formula, what we get is 60 plus 23.5, so 83.5 divided by 2, that will give us 41.75 degree, divided by a by 2, which will give us 30 degree. So again, using trigonometric table, sine 41.75 degree, it's approximately 0.6659 divided by sine 30, that's half, 0.5. So students, it comes out to be about 1.33. Actually, it is slightly less than the refractive index of water, right? So refractive index of vinegar is almost same as that of water. So this is how the refractive index of different liquids which we fill in the hollow prism can be determined experimentally. This is what we have done, the entire investigation, studying the refractive index of various liquids and plotting graph between angle of incidence and the angle of deviation.